Morning, afternoon, or evening. Hey, we're in physics here, and we're going to be looking at a little bit more on conservation of energy problems today. We're going to be looking at maybe an example or two more of friction involved with conservation of energy, and a little bit and then we'll get into power, I guess. So we'll split it into two major parts this morning, or afternoon or evening, depending on when you're watching here. So once our Blackboard opens up, we'll just kind of go through what we're going to go today. There we are. Okay, so getting close to the end, we've got this. I want to do a little bit more on conservation of energy. Then we got power, and then that's basically it. Power and cost of power are the last two topics in this unit. So we'll probably finish this unit in the next day or two. And then we'll have our hand in, of course, and then also there will be a quiz in there as well. Okay, so let's get our ideas here for today. So today is day 14 in Unit 2, and we're going to be looking at more examples of energy conservation. And we looked at maybe two major types of energy conservation: sliding down a ramp or hill and falling down through air resistance. Today we're going to be looking at maybe a couple of different examples that still use friction and friction. And then if we have time, and we probably will, we're going to look at the intro to power. Okay, the relationship between work, power, and energy. Okay, so let's start off with a simple example of another energy conservation question. So let's say an arrow with a mass of 0.180 kilograms is shot at a velocity of, let's say, 39.5 meters per second. Okay, and the arrow strikes a block. So there's a block sitting on the ground. Okay, so it strikes a block with a mass of, let's say, 12 kilograms, 12.0 kilograms. It's sitting on a surface with a constant of friction of 0.250. Once the arrow strikes the block, how far will the block slide with the arrow in it? Oops. How far will slide? So obviously, this block is going to slide, and then it's going to be stopped by the force friction. So in our case, we have this kind of a situation forming here. If we draw it out a little bit to help ourselves. Okay, so if we have our surface, and we have our target block here. Okay, and it has 0.25 and a velocity equaling of the target block of 0 meters a second. And this arrow is coming in here at 39.5 meters a second. Okay, and we want to know, well, and it has a mass as well, 0.810. And then after, what we're going to have after, we're going to have an after situation where the block and arrow are going to be together like this. Okay, so that mass is going to be both of the masses together. We should have put the mass of the block up here too. So the total mass is going to be 12.180 kilograms. And we're going to have a velocity of something. Well, actually, we don't need the velocity because we don't want to find the velocity. We want to find how far it's going to slide. So we're going to actually find how far this is going to move, this distance. Okay, and we know the friction equals 0.25. Okay, and the mass, actually we do need, we do have the mass up there, I already put it there. Okay, so what's going to happen is this total momentum here, or total energy of this system, not momentum, pardon me, this total energy of this system is going to be the same here and here. And now all of that energy is going to go into the work done by friction to stop the block in the bottom here. So what's actually happening is at the top, we take the kinetic energy of the arrow, right? Doesn't have any gravitational or elastic energy. And we add it to kinetic energy of the block, which is 0. Because it's not moving. And that's going to be equal to the work done by friction to stop it. We could find out how fast the block is going to be going right as the arrow strikes it too, but we don't need that right now. We could use momentum for that. But in this type of question, we want to find out how fast, or not how fast, sorry, how far it's going to move. Okay, so that's kind of what we're going to do. So we know that this ends up being 0. So then we can plug in our results. The mass of the arrow times the velocity of the arrow squared over 2 plus the 0 is going to equal force of friction times the distance. Okay, so now we have to first find the force of friction. So the force of friction is going to be mu times m times g. And this m is going to be the mass of the block and the arrow together because we're looking at the total mass here. So in our case, that's 0.25 times the mass, what did I say, 13? Didn't I say it was 12? Yes, 12, pardon me. So this should be maybe right there, 12.180. Kilograms times 9.8 meters per second squared. Okay, and that's going to give us the force of friction that's going to help stop the block. So if we do that, we multiply those together, 0.25 times 9.8 times 12.180, we get a total 29.841. Okay, so then we can plug in our numbers to solve for the distance. We've got this we've got this, and we have to find that. So our mass of the arrow, 0.180 kilograms. Our velocity of the arrow, 39.5 meters a second squared. And square that up. Or not squared, meters a second only, pardon me. So velocity divided by 2 is going to equal 29.841 times d. Okay, and we solve for d. So let's go ahead and work out on the left side. 39.5 squared times 0.180 divided by 2. Okay, and you get 140. 140.4225 joules equals 29.841 times d. So divide by 29.841. Okay, and we get 4.70 for d, meters. So that's how long it would take the friction force to stop that block. Okay, a different type of energy conservation question from what we did yesterday. Just wanted to add in another example that you might see come up on the hand-in or something like that. Okay. You're looking at my background notes. There's a ramp one here. We did one like that yesterday. We also did one that went down, dropping down through the air. So those are the main three types, I think. So we're probably good there with conservation questions. Just wanted to add that extra one in there. So that brings us to power now. So if we look back, do that little extra question. Now we'll look at power. So let me just bring up on my other side here my background of power, and we'll start with going through what we mean by power and its relationship to energy or work. Okay, what it means in terms of definitionally and equation-wise, what's the unit that we have, and that kind of stuff. Okay, so let's flip that over in the next part here. And the second thing we want to look at today is power. Okay, so the easiest way to define it is the amount of work done per unit of time or energy done per unit of time. Because remember, work and energy are the equivalent units. So it's the amount of work, which we'll put in brackets, energy, done per unit of time. And the unit of time that we use is a second. Okay, so energy over time. If we look at that, we'll have 1 joule per second. And energy over time equals 1 watt. Okay, so that's the unit of power. Okay, 1 joule done per second gives us 1 watt. Okay, we do a lot of times we get into the kilowatt area. Okay, formula-wise, it's very simple. If we're talking power, we'll use P. Don't get it mixed up with momentum. Momentum has an arrow over top, or capital P is vector. So we'll call this power, and it's measured in watts. That's basically a change in energy over time, or a change in work over time. So change in energy or, that's an E, by the way, change in work. Okay, and Those are joules, both measured in joules. Okay, and then this last one, T equals time, and that's measured in seconds, usually. Okay, so if we want it in watts, we have to make sure it's in joules and seconds. So that's the equation for power. So the relationship between power and energy is that power is a rate of how much energy you use per second, basically. Okay, so the more energy you can put output per second, the better. Well, the more power you have, I guess, not necessarily better, right? Because if you're paying for it, like electricity or something, it's not better, right? Okay, so let's look at some examples of power equations that we will see. Often we'll be looking at kilowatts as well. So remember that kilo means 1,000. So if I say something like a kilowatt, then got to keep in mind the relationship between just like kilometers and meters. It's the same thing. Okay, so let's look at some examples. We'll start off with some real simple ones, just simple calculation of power, and then we'll add in some more complex ones as we go here. Okay, so let's say like a hair dryer is rated for 1,500 watts. Okay, that's a typical wattage for a hair dryer. If you dry your hair for 5 minutes, how much energy do you use? Let's say 5.0 so that we get two significant figures. There we go. So this is pretty simple. We're just a straight application of the power formula. We've got the power given to us. We've got the time given to us. Okay, the thing we have to be careful of here, if we're calculating this out, okay, good, is this is in minutes. So 5.0 minutes times 60 seconds in a minute to change it to seconds. So that's 300 seconds. Okay, so we have to be careful with that, and that's our time. Okay, and then this is our power here. Okay, it's already in watts, so we don't have to do anything. So if we know that power equals a change in energy over time, okay, we can just simply multiply both sides by T. So a change in energy is equal to power times time. So in our case, it's really quite simple. We take the power of 1,500 watts and we multiply by 300 seconds. Okay, now a watt is a joule per second, so the seconds will cancel out and leave us with joules. So when we multiply these two together, you get 45 with 4 zeros. That is a heck of a lot of joules, which equals, if we write it in kilojoules, it's divided by 1,000, it's 450 kilojoules. So 450,000 joules of energy just for drying your hair. So joules, if we think about the electricity that you're using there, it seems like a lot, but you'll find out later that when we pay for electricity, I think the rate now is something like, I think it's like 14 cents per kilowatt hour, which a kilowatt hour is about 3.6 million joules. So 3.6 million joules cost you usually about 15, 16 cents here in Saskatchewan right now. Okay, so that's a real simple one. Let's do a combination power question with work or energy. So let's try combining it a little bit. And we'll do a couple like that. Okay, just checking we're on 20 minutes. So we'll do maybe another 15 or so. We'll do a couple more examples like that. So let's go ahead and try one that's using an example with a combination. Okay, so let's say let's do a winch or something like that. A winch pulls with a force of 345 newtons, moving a trailer forward 6.78 meters in 25.0 seconds. Okay. What is the power of the winch if it's at max output? Let's say, period. What is the power of the winch if it is at maximum output or max output? Okay, so we've got work done here. So we know that power can be change in work over time. So if we're thinking about that, oops, not that one. Okay, so we've got a situation where we're going to be using power is a change in work over time this time. So this is a force, and this is a distance, and this is a time. So obviously we've got to find the work first. So that's force times distance. So we know that work equals force times distance. Okay, and that all of the force is in the same direction as distance because it doesn't have an angle or anything like that. So we'll do the work first. So that would be 345 newtons multiplied by 6.78 meters. And that's going to give us joules or Newton meters. Okay, so if you take your calculator out and multiply 6.78 times 345. Okay, we get 2,339.1 joules. Okay, now that we've got the work done, we have the time over here, so we just can calculate power in our second step. So take your 2,339.1 joules. Now we want to be rounding off to, looks like 3 significant figures in the end here. And this will give us what? So divide it by 25. And you get 93.564, so 93.6 watts. Or, yeah, 93.6 watts, or joule per second, which is the same as a watt. So there's an example where you're doing a combination of work and power together. Okay. Obviously, we can get some other questions where we combine, say, gravitational energy or kinetic energy or elastic energy in there as well, because you can have examples that use energy. So let's do one with a typical example with gravitational potential energy. Lifting something is very common. Lifting something off the ground requires power. Okay, so we'll do that on the next one. So you might see one that looks like this. Okay, let's say an electric motor, we'll say. Is rated at 200.0 watts. How much time, we'll say, how much time will it take the motor to lift, okay, let's say it's powering a lift or something, a crate with a mass of, let's say, 105 kilograms up 1.80 meters. And we're going to assume a couple of things here. And, so 100% efficiency, which isn't the case with electric motors. Sometimes they warm up and get heated, and some of that energy goes to heat, right? But we'll just assume that it does 100% efficiency. What's the quickest it can go? So in this case, we're using a power energy form. So we're looking at power equaling a change in energy over time instead of a change in work over time. So, and we know that the energy that we're going to have is we're creating gravitational potential energy. Okay, so we've got our mass of the crate. We've got our gravitational, we've got our height of the crate lifting and the gravitational constant of the Earth. So that will give us our energy, and we also have the power rating for the motor. Sorry, guys. So this is where we're going to calculate. So first we'll calculate the energy, put it in the change in energy part, put the power in, and then rearrange it and calculate time. So our first step is to get our energy. So we've got our crate mass, the Earth's gravitational constant, and the height lifted. Okay, so we take our calculator and crunch those together. 105 times 9.8 times 1.80, and we get 1,852.2 joules. Okay, and then we can use the power equation. We know that power is 200 watts. 4 significant figures, 3 significant figures, and 3 significant figures. So we're going to round it off to 3 significant figures. Our energy is here. And here we have our time on the bottom. So how do we calculate this one? Well, we have to rearrange it. Times the time over here and then divide by 2. So T is going to equal 18.52.2, right? Divided by 200 watts. This is joules, and divided by 200 watts. Okay, so if I take my calculator, go divide by 200, I get 9.26 or 9.26 seconds to 3 significant figures. It's going to take that long to lift it. So there's an example of using power with an energy. And in this case, it's the energy of gravitational potential energy. Okay. Okay, let's check our time here. We got enough time to squeeze one. Yeah, we do. We'll squeeze one more in. We'll do an example that uses another energy calculation, and we'll do a change in energy, okay? Like a car driving forward, and then say it applies its brakes, and we're looking for power there. So let's do one more that uses that, and then we'll call it a day. Okay, we'll flip this one ahead. So this is the fourth and final example with power, and we still have one more thing to do yet, though. You still have to talk about cost of power, electric power, and stuff like that. And then we're done the unit in unit number 2, which it's about half as long as the first one that we did, the big long one. Okay, so let's do one with the car. So let's say a car. So this one's going to have a change in energy. So I'm going to give 2 different sources of energy for this one. Okay, so there's my example. Sorry, I had to readjust my screen on the other side there. Okay, so it goes something like this. A car traveling at, let's say, 28.5 meters a second. Okay, and brakes to slow down. After 5.5 seconds, the car is only traveling 12.2 meters a second. And what is the power of the brakes applied? Power of the brakes. So in this case, we have a change in energy. We don't have it going all the way down to 0. So we have the car. Oh, we do need a mass of the car too. What is the power of the brakes if the mass of the car is 1,115 kilograms? So what we have here in this case is we have this car slowing down. So we have it going 28.5 meters a second, and then it's going to go down to only 12.2 meters a second. So there's going to be a change in energy. So we have to go mv squared over 2 minus mv, we'll call it b for the second one, squared over 2. And that's going to get our change in energy. Okay, that's what we want. This one doesn't go all the way down to 0, so we can't just use one equation. We have to figure out what the change in energy is. Okay. Okay, and obviously there's going to be, you could just kind of figure the difference in the velocity out as well. That would work. Okay, so in this case, we've got 1115 kilograms. We should probably put that in there, times 28.5 squared over 2 minus 1115 kilograms times 12.2 meters per second squared over 2. The change in energy. So if we do the change in energy like that and see what we get, okay, 28.5 squared times 1115 equals that divided by 2. So we get huge numbers here. Lots of joules in that one. And this one here Okay, so we get 12.2 squared, okay, times 1115 divided by 2. Let me check the first one, just in case I didn't square it right. 28.5 squared times 1115 divided by 2. Oh, I'm good there. Okay, so when we subtract 2, we get 369.851. We'll just go to the nearest joule is our change in energy. So that's quite a big change in energy. Okay, so then if we're doing power now, we want to know what is the power of the brakes. We've got the change in energy and we've got the time here. So now we can apply the power equation. Power equals change in energy over time. In our case, it's 369.851 joules divided by 5.5. And that's going to give us something in watts. Okay, two significant figures, I think. Yeah, because of the 5.5. So we'll round it off to 2 when we're done. So divide that by 5.5. And you get two significant figures, 67,000 watts, or if you like, 67 kilowatts. Okay, Watt's named after James Watt, so that's why it's capitalized W. It's named after a scientist. And that's 4 different kinds of power equations using changes in energy, changes in work, and so forth to figure out different various problems. So that pretty much takes us close to the end. We've got one more concept left, and that's the cost of power. But I'm going to save that for next day because we're already into the 38-minute range, which is good enough for a class. I have some schools only have 45-minute classes in their schedules, so I try to keep the videos down to a reasonable length. Okay, so I'm going to stop here today. We'll finish up tomorrow with the cost of power, and then we'll probably start the hand-in for this unit, and then we'll do a review after that, and then we'll have our quiz, and then we're going to get into our next unit, which is fields. See you tomorrow.